Hello and welcome to Otten Math. In this edition of Otten Math, we're going to talk about solving polynomial equations by factoring. So let's step back and talk about solving polynomial equations. So if I have some polynomial which I've factored, x minus 2, x minus 4, x plus 1 squared is equal to, we'll say, 0, then the factors are going to be x minus 2, x minus 4, put a comma here, x minus 4, and x plus 1. So those are the factors of the polynomial. The roots or zeros are going to be the values of x that make y equal to 0. We've already set the equation equal to 0, so the roots or zeros are going to be plus 2, plus 4, so 4 minus 4 is 0, and negative 1 are the zeros. Multiplicity is the number of times that a given root is repeated, and so when a root is repeated more than once, we want to state that multiplicity. If it's just repeated once, there's only one root of a given integer, and then typically we're not going to state its multiplicity. I know that I have a multiplicity here of 2. I have 2 roots at negative 1. So I can, if I were to express this fully, it would be x plus 1 times x plus 1 times x minus 4 times x minus 2. So we have a multiplicity of 2 for x is equal to negative 1. And then we're going to find the x intercepts, and the x intercepts are going to be 2, 0, 4, 0, right, 4, 0, and negative 1, 0. All right, so these are all related relative to how you graph a polynomial, but we're asking for different values and ways to express similar things. So factors of the polynomial relate to the roots or zeros. We can get the multiplicity based on our factors, and also the x-intercepts. The x-intercepts is a coordinate, not just a value for x. All right, so let's move on and talk about the objectives. We want to be able to factor and find the zeros of polynomials by grouping terms. We want to use quadratic factoring skills to factor and find the zeros of quadratics that are disguised as polynomials. And then the last one I'm going to add here is we want to use the rational root theorem to solve polynomial equations and to reduce the polynomial to a quadratic for further factoring. All right, so those are our objectives for today. So let's get started. Let's talk about factoring by grouping. So we're going to factor by grouping x cubed plus 5x squared minus 4x minus 20. So we're just going to go through. I'm going to go through one. You're going to go through the other. Let's talk about what I'm doing here. I'm going to group the terms. So I've grouped x cubed plus 5x squared. I removed a common factor in x squared times x plus 5 times minus 4 times x plus 5. I factored by grouping here. So x cubed plus 5x squared was one group. Minus 4x minus 20 was another group. I distributed out the common terms x squared and minus 4 from the two separate groups. I am going to rewrite this factored grouped form into two binomials, x squared minus 4 times x plus 5. This is a difference of two squares here, so I'm going to factor that further. And then I'm going to find the roots x is equal to 2, negative 2, and negative 5. You can take care of the next one. I'll pause here. All right, 3x cubed minus 16x squared minus 12x plus 64. Factor by grouping 3x cubed minus 12x minus 16x squared plus 64. I'm going to factor out the common factor here, 3x times x squared minus 4. Factor out negative 16. Remember, this is a plus here. It changes to a minus because we've distributed out negative 16. X squared minus 4. I have, again, the difference of two squares. 3x minus 16, the root for that is 16 over 3. X minus 2 times x plus 2. Root is plus or minus 2. All right, so now we're going to we're going to change to polynomials that are quadratics in disguise, and we're going to factor and find the zeros. So the pattern here is x to the 2n plus or minus x to the n plus or minus some constant. So I have a trinomial here. The first term has an exponent that's twice the value of the second term, and then we have a constant. So 2x, x, and then the constant. And we're going to go ahead and solve this as if we were solving or factoring and solving a quadratic. All right, so I'm going to think of 2x to the fourth minus x squared minus 3 as 2x squared minus x minus 3. Factor it as if it were a quadratic, and then I'm going to reapply the proper exponent value to bring the factored quadratic to be or have that relationship and to equal the straight polynomial, unfactored polynomial. So I need to add 2 here, these values of x. We know that when we multiply a variable with an exponent, that variable, we're going to add the exponent values together. So 2 plus 2 here is equal to 4. So I end up with my factored polynomial, but originally I thought of it as a quadratic. Okay, I'm going to have you take care of the next two. Let's come back and have you take a look at your work. I'm going to end up with 2x squared minus 3 times x squared plus 1. I'm just cutting to the chase here, factoring and reapplying. Solving for x, I end up with x is equal to plus or minus root 3 over 2, or x is equal to plus or minus root 6 over 2. And then I'm going to end up with x is equal to plus or minus I. Okay, next one, x squared minus 6 times x squared plus 2. Solving, I end up with x is equal to plus or minus root 6. And let's take the 2 off here. And then solving here, I get x is equal to plus or minus I root 2. Okay, last one, x to the 6 minus 7x cubed minus 8 is equal to 0. X cubed minus 8 times x cubed plus 1 is equal to 0. And then I'm going to solve x is equal to 2, x is equal to negative 1. All right, so last thing we're going to do, this is part 3 of our objectives. We're going to use the rational root theorem to find the possible rational roots and solve this polynomial using that theorem. I'm going to have you take care of this. I'm going to pause here because we've done some practice. All right, so we find the possible roots, plus or minus 1, 2, 4 over 1, 3, plus or minus 1/3, 2/3, 1, 4/3, 2, and 4. My suggestion is to try the integers from smallest to largest, and that's what we're going to do. So we're going to try 1. That doesn't work. So remember, we have a placeholder here in 0, right? We don't have any x term, so we have to put that placeholder here. We're going to try negative 1. That doesn't work. Using synthetic division, because ultimately we want to have that polynomial result. 2 doesn't work. Negative 2 does work. All right, so now we're left with a cubic polynomial. And so the common mistake is to think that negative 2 is now no longer a possibility for a root again. But in fact, we have a double root in negative 2. I try negative 2 into the system using synthetic division. I end up with finding a root and a quadratic, which I'll now factor 3x squared plus x minus 1. We're going to have to use a quadratic formula, and then we're going to end up with minus 1 plus or minus root 13 over 6. Okay, next one you're going to do. I'm going to pause here. All right, possible roots, this is pretty straightforward. Plus or minus the factors of the constant over the leading coefficient. Plus or minus 1, 2 over 1. Plus or minus 1, 2. We're going to try plus 1. That works out. We're left with a quadratic. We can factor this quadratic pretty quickly. X plus 2 times x plus 1. So the zeros end up being plus 1, minus 2, and minus 1. All right, so you're going to take care of this one. I'm going to pause here. Okay, remember we just need to find 2 zeros. We're going to list the possible rational roots, again, not the complex roots. This just gives us the possible rational roots. Here they're listed. I'm going to try 1, doesn't work. Try negative 1, that works. Try negative 1 again, I have a double root. I factored here x plus 1 times x plus 1, and then I'm resulting with a quadratic. I'm going to factor the quadratic and then find my zeros. And so we've fully factored and found the zeros for this polynomial. All right, you take care of this one. If you notice, this is the same one that we did before. You find x is equal to 2 and negative 1. I'm going to give you another one to solve. This is the last one. All right, I've already given you a hint here, but I want you to factor using, I'm going to take this out. I want you to factor using the rational root theorem. Okay, so okay, we can factor by grouping, yes. All right, so yeah, factor by grouping. Okay, so factor by grouping, that's fine. Now we're going to try this next one. We're going to try to solve this by using the rational root theorem. Again, we just need to find one root. Here are the possible roots. Doesn't work. 1, -1 doesn't work. 2 doesn't work. -2 doesn't work. -3 doesn't work. 3 doesn't work. -4 doesn't work. 4 doesn't work. All right, 1/3 finally works. And then I've reduced this to a quadratic. I'm going to go ahead and rewrite my quadratic 3x squared minus 36. I'm going to distribute out 3. 3 times x squared minus 12 is equal to 0. X squared is equal to 12. Solve x is equal to plus or minus 2 root 3 over 1/3. So you can see we spent a lot of time using the rational root theorem when in fact we could have factored by grouping. So this just goes, so we did have this problem before, but I wanted to show you sometimes you can eliminate a lot of work if you can factor by grouping or find a product pattern quickly within the polynomial rather than having to go through a host of guess and checks for rational root theorem. Anyway, that's it for this edition of Ott in Math. Come back and join us when we talk about the complex conjugates theorem. That'll be our last session for Chapter 2, next edition of Ott in Math.